Okay, so you may have looked at the first one talking about Mikael Pedersen and the other one just as a general overview on the bike. But I find this bike particularly engaging on, there's a number of different elements. So I thought we'd split it down into a few other elements. So at the moment I'm going to talk about the fork in this construction, how they work, and then I will talk about the bottom bracket and what's interesting about that. The saddle, which is enormously important to the bicycle, and probably the reason for this bicycle to exist started with the saddle and then the gearbox. But obviously you're all used to seeing a fork, and the reason that a normal bicycle fork like that has got a shape to it, it's to let the wheel self-align, so it's what we call caster angle. So it means that the wheel it's like a supermarket trolley. That's the easiest way of describing it. So the center point of the wheel will be slightly ahead of where the angle of the fork is, and that lets the wheel continue in a straight line when you take your hands off. So this initially doesn't look like it's got caster angle because this member here tends to give you a feeling there's too much wheel forward or forks forward. Well, actually the caster angle is taken between the top and the bottom bracket, so it's coming down here. So it's a peculiar thing to look at, but what I'm really interested with this is this as a sort of point of study kind of explains what Mikael Pedersen was doing, which was simply using material in compression and tension. So if you just simply look at the way that the fork is constructed and think of the weight of somebody bearing down with their weight onto the bike that's been resisted by the ground, it's obvious to anybody where the fork wants to do, how the fork wants to bend. This wants to bend up as that pushes down. So what we've got here is the top members that are all working in compression, and this member here and that member there working in tension. So i.e. one's being pushed and the other's being pulled. And it's kind of, if you think of a pen here, it's a good example that a bit of material in compression just does that. But in tension, I could probably swing on that and it will hold me. So material in tension is extremely strong. In compression, if it's a tube, it's equally quite strong, not as strong, but if you can keep a continuous motion on that bit of material and not let it flex, it will take a great deal of strength. And that's why the center bridge has been made, and that then keeps this thing all in one line. So compression and tension. So that is the principle that he is using for his bicycle. And again, if you just have a look at that, you can see compression and tension is all happening within one piece of metal. So this is being stretched as that's been compressed. So theoretically not a very pure design, because the metal all the time is having to flex and work. So he's sort of gone back to really very basic principles of making something strong. The material used here is so thin. He did a racing bicycle that you could squash the material, the steel, with your fingers. So it's not a heavy bike. The whole frame weighs 1.8 kilos. So it's a lightweight bicycle. It just looks clumsy because it's got a lot of material, but it's very lightweight. So his construction, as we've described here, the patent, he applied for 2 patents. The first one was 1893, I think, which was a partially wooden built machine. But by 1897, he's laid out patent drawings for this frame, and it's pretty much untouched or unchanged since the initial patent went in for this design. And he did get it right. The only thing that changed was the handlebar position. Earlier bikes had the handlebars mounted down here and came up here. The later bikes had these, but in principle it was the same thing. So when we look at the bicycle again in detail, and you come right into this head detail here. Now this is quite exceptional. So you've got 4 tubes all coming in together and then all wrapped into this with this steel casing around here. Now this steel is a very thin plate steel that, as you can see there, is all soft soldered in position. So there's no silver solder here. I suspect the tubes have a bracket in the center that was originally silver soldered, and this was put on afterwards. Now, I've had a really good look at this top cover, for want of a better word, and I can't see a joint in it. One would expect to see a silver soldered or brazed joint going through it, and there's no sign of any joint on it. So I can only conclude that this was some sort of very clever pressing or forging, or maybe it was spun as a collar and then cut out afterwards. I honestly don't know how it was made. Either way, however they made it, it was bloody well made, and it's a beautiful thing. So at the top then you've got some very, very simple ball bearings compressing in there that gives you your ability to steer. Nothing particularly complicated. That's all pulled down by this top bracket that holds it. When you come down to this center bridge, again, that's a very interesting piece. They've cut every bit of metal out of this that they could. So they've obviously relieved it in the center for the brakes to operate. But what's interesting here, and I quite like this is silver soldered to this tube. And where the silver solder, which is obviously a non-ferrous material and therefore quite stable, has been nickeled, where it's been nickeled over the top, the nickel is retained in this area here, and whereas the steel, the ferrous, it's a ferrous oxide, it's always wanting to oxidize, so it's thrown the nickel off. You can see some nickel showing still in the lower parts of it here, but wherever you get a heavy deposit of nickel, the likelihood it was either very greasy or it's a non-ferrous metal, i.e. soft solder or silver solder. So this is a silver solder joint here. Now, in the center of this point here is a pivot, and most people who've worked on these bikes will never understand how clever and what they've done with this pivot. So I'm going to do a little drawing here, and it's pretty straightforward, and excuse my inability to draw, but you've got a fork on the frame. So in effect, the frame has a top section and a bottom section that all come back and terminate back onto the frame, and then this center bridge sits in the center here with a little collar on the top and the bottom, so that this piece here, the center piece, can pivot on this. But the way it's done, and you can see on this, it's got a lock nut here and a lock nut on the bottom and an adjuster. This whole central piece here sits within this section here and to here. So what we've actually got in the center of that, which is the most amazing little bit of engineering, is a tapered pin like so with, I think offhand, I believe that's a quarter BSF and that is 5/16 or vice versa. So you've got two separate threads. So you've got a thread up the end of these and a thread up here. And at the top of it, fixed to it, you've got this little square nut that sits on and enables you to adjust it. So that can then turn backwards and forwards. Now, as this pin goes in, it does mean that the threads on the top part and the bottom part have to be indexed together because it winds in as an entirety. So as you pick up the threads here, they equally need to pick up there. So the machine that put the threads on here didn't start randomly and put a thread on there because it would have never tied up with that. So you couldn't put it in. So the threads are indexed here, and the threads and the top and the bottom of this fork are equally indexed together. So when the pin goes in and the fork bridge here sits onto that pin, it enables you to move the fork bridge up and down as it sits on the collar, and that then brings the fork up to sort of bring enough pressure back onto this top bracket that's been set up beforehand. So we're not pulling away from the bearings at the top. So it's been held here. And equally, to make it just that much more special, and only Pedersen would seem the need to do this, this is out of a bit of mild steel, but there is an insert in this collar here that's out of a bit of high tensile steel, so that it wears this and not that. So the fork is never taking the tension. it's going through this little pin in the center. So it's a sort of a funky little detail that is not really noticed by most people, but to me that sums up the sort of what was going on in this guy's mind. It is beautifully simple, but it's only inevitable and obvious after you've invented it. You know, it's very, very clever. So push on down the forks. The lower part of the forks, again, it's just a fabulous design. So what they've done here, they've split the top fork and they've compressed the bottom fork. So the top fork then goes over the flat of the bottom fork to create this lower bracket. And then behind this washer and nut, they've spot faced the tube to ensure that you've got a completely flat surface for the nut and the washer to sit on. But if you look at the nut and the washer, it's all nickeled, bar turned, it's chamfered at the top edge, square at the back edge. I mean, it's beautiful. And then this little thing in here is an oiler. So you twist it around like so. I don't know if you can see it. You twist this and you can then oil the axle and then let it go back. Now that was made by a company called Rotherham's. And I'm going to get deep into Nerdsville here. Rotherham's were going since about 1750, thereabouts, long time ago. Birmingham-based company. They were clockmakers, then they became precision engineers, really. They made a number of things. At the time they were making oilers, flip-top oilers, drippers, they were making bonnets and speedos, they were making extraordinary numbers of things. They had something like 400 people directly working for them, making components like that. And then apparently they had another 100 or 200 people outsourcing this stuff. So this gives you an idea of the size of the industry of making things in this country back in about 1910. You know, it was a big, we were making a lot of stuff. So yeah, Rotherham's, look out for that name. You'll find it on lots and lots of components. They're beautifully made components. So we've gone from the bottom, the middle, the top, so we have all that sort of together. The final part of it that isn't particularly groundbreaking, it's just beautifully executed, and that of course is the brakes. So on the brakes you may have noticed the handlebars have got these brakes coming out of the wrong end of the handlebars. By most people see them coming out here and going the other direction. So inverted levers. And the reason for this, it's one, very nice to use, but secondly, you are free of cables. So the cabling comes up through the handlebars and then back down through the head. So any movement that you put into the brakes is transferred all the way through here into these rods coming down to here. So, you know, a really clean and nice system. But then when you start to look at the brakes itself on the bike, this is completely original. It is an exceptional bike from its condition point of view. But the fixings, they're all square-headed and slotted so they can be adjusted with a spanner. These are sprung steel, and that enables, these aren't set up quite properly, that enables the pressure that's imposed upon them, I guess is the word, by this bracket here, to make sure that they always pull back away from the rim. So there isn't a return spring on this, they're relying on these two forks either side of it. But if you just look how, you know, it's stunning. I just think it's gorgeous. So there you go, guys. Sort of a bit of a deep dive into the front end of a Pedersen bicycle. We'll carry on and we'll do other things, but that's the forks covered, I think. Thank you.